Unit 4, Earth Systems and Resources. We're in Module 22, Earth's Atmosphere, Global Wind Patterns, Solar Radiation, and Earth Seasons. This is a long module, so buckle in and sit tight. In this unit so far, we have examined Earth systems, including formations of rocks and soils and the role of watersheds. And now we move on to learn about the creation of climates by movement of air and precipitation. In this module, we'll explore why incoming solar radiation, known as insolation, which is the main source of energy on Earth, differs at different latitudes and how it changes with the seasons. With this knowledge, we will focus on the planet's atmosphere, starting with an exploration of atmospheric gases and different atmospheric layers above Earth's surface. We will consider how solar radiation and its properties of air combine to cause air to circulate in the atmosphere. These air currents bring warm and cold air to different regions. They also move water vapor around the planet, which causes some regions to receive more precipitation than others. In doing so, this air current determines the locations of different climates, the location of terrestrial biomes, and prevailing directions of winds across the globe. So our five learning goals today are: explain why the amount of solar radiation varies with latitude and the seasons, identify the major gas and layers in the Earth's atmosphere, describe how the properties of air determine patterns of circulation, explain what drives the atmospheric convection currents, explain how the Coriolis effect alters the globe wind directions. So our first standard, incoming solar radiation, is called insolation. Is Earth's main source of energy. So we get our main source of energy from the sun. You probably already knew that. Along with solar radiation, air's properties allow for atmospheric circulation, bringing warm and cold air currents to different regions. Solar radiation varies due to Earth's curvative and tilted axis. So we're the fact that we're a sphere and we're not straight up and down varies how much sunlight hits parts of the Earth. The area near the equator, the tropics, receive the most sunlight, while the poles receive the least amount of sunlight. Since the surface area of the equator and the poles differ, the amount of energy per square meter differs. This is due to a difference in latitude. We'll look at that in just a second. And some of the light that reaches the surface of the Earth is reflected back. This is known as albedo. So this is a graphic about albedo, and so you can see that color plays a big part on how much energy is absorbed versus sent back. And the lighter colors are going to reflect back and absorb less. The average Earth's albedo is 30%, but you can see like sea ice, so up near the Arctic area, is going to shoot back about 50 to 90%, whereas our asphalt's going to soak it in. Our forests, the dark green forests, are going to be able to soak in a lot more. Our fresh snow sends a lot of it back. Clouds send a lot of it back. So, of the Earth's radiation, there are different amounts of radiation that the Earth absorbs depending on what color it is. Besides solar radiation and latitude, Earth's tilt causes seasons. One side of the planet is tilted more closely to the sun. That's the summer season, while the other is in winter, and vice versa. So looking at this graphic right here, we can see that the Earth is on a 23.5 degree tilt. And obviously the part that is tilted more towards the sun is going to be a little bit warmer during that part of our our rotation around the sun. And we have different solstices and equinoxes. So the sun is directly overhead the equator of all regions of the Earth, receiving 12 hours of daylight and 12 hours of darkness, and that's when we perceive spring to start, especially here in the northern western hemisphere. So that's us. The June solstice, the northern hemisphere, is maximally tilted toward the sun, experience the longest day of the year. So our summer solstice is the longest day of the year, so we have the most amount of sunlight. Our December solstice is when we have the least amount of sunlight here in the northern hemisphere. And then September is our fall equinox, or the opposite of the March equinox. So, depending on where you're located in the world and how it's tilted towards the sun, definitely depends on how much sunlight you're getting and why the seasons are as hot or as cold as they are with the amount of sunlight. So, right now, we're facing kind of towards away from the sun. We're tilted more towards not the sun, even though we're rotating, and that's why our days are getting shorter. And they'll get shorter until the middle of December, and then after that they'll start to get longer until we reach the March equinox. So now we're on our second standard. So identify the major gases and layers in the Earth's atmosphere. The atmosphere of the planet is comprised of several gases, with two being primarily nitrogen gas and oxygen gas. The other gases in the atmosphere are considered trace gases, only found in very small amounts. Carbon dioxide, methane, and nitrous oxide, and others. We'll look at that in just a second. And many of the trace gases are greenhouse gases, so while they're relatively small, they still have major impacts. So looking at this graphic, you can see that nitrogen is very big, or very takes up a lot of our atmosphere, and so we know that our atmosphere is a nitrogen sink, and then oxygen makes up a good part of that, and our other gases is 0.97%, so less than 1% of the rest of our atmosphere is made up of other gases. But even though they're trace amounts, they still play a big impact, such as carbon dioxide and global warming, which you're already familiar with. The gases in the atmosphere are separated into 5 distinct layers. These layers are held in place by gravity of Earth. As gravity increases near the surface, more molecules of the air are found in lower layers. So the layers of the Earth are the exosphere, the thermosphere, the mesosphere, the stratosphere, and the troposphere. So closest to the Earth is the troposphere, 0 to 16 kilometers away. Stratosphere is 16 to 50. Mesosphere is 50 to 85. Thermosphere is, again, 85 to 600 kilometers. And we have the exosphere is 6,000 to 10,000 kilometers. And after that, you just get into regular old space. If you don't know what a kilometer is, the best way I can describe it to you is it's a little bit smaller than a mile. Okay, so if you have an idea what a mile is, you know how far up that is. Okay. And so the layers are held in place by gravity. And what that means is that the molecules in the air will have a gravitational pull. And so the heavier molecules will stay closer to the Earth, whereas the lighter molecules are still being pulled by gravity, but they make up those higher end of our atmosphere. So looking at it here, you can see that each atmospheric level has like its own temperatures. And as you're getting close to Earth, the closer to Earth you are, the kind of cooler you are. So we see that the troposphere is like a little over 20 degrees Celsius, which is, in the 70s, 80s degree range, all the way down to that negative 60. And then as you go up, it varies a little bit. And then once we get to the thermosphere, we reach really high temperatures all the way to the exosphere. And that's because of how much radiation the gases layers are absorbing from the sun. So all of these layers are kind of protecting the Earth from UV radiation, which is increasing its temperature, which is good for us because it means it holds our temperature in. That's part of one of the reasons why our atmosphere is so special, because it does keep us warmer, because it blocks a lot of that, it takes a lot of that radiation from the sun and keep that warm air trapped in. Right now, it's not that great of a idea because we're getting more carbon dioxide built up here, so we're becoming too warm. So the troposphere, being the closest to the surface, contains the bulk of our particles, has an immediate effect on species through climate and pollution. Okay, that's, again, the area that's at the bottom. The stratosphere is directly above the troposphere and is less dense, but it's the location of the ozone, or the O3 layer, which absorbs most of the UVB, or the ultraviolet radiation, and all of the UVC radiation. These forms of radiation can cause DNA damage and cancer in organisms, so they will, for people with lighter skin, they don't have as much protection against the sun, and they will cause DNA damage that will prevent the cell from going through its fixing processes and become cancer. The mesosphere is the layer where most of the meteors burn before reaching the Earth's surface. The thermosphere is important for blocking X-ray and some UV radiation, and the exosphere is where satellites orbit the planet. So the bulk of our ozone is the UVA, UVB blocking. Some of the UVA and UVB do make it through, but a lot of it gets blocked here. This is where satellites hang out, so like 600 kilometers away. The thermosphere blocks the X-ray, so I don't think we quite understand or can't quantify how powerful the sun is, but it's giving us X-rays, okay, and that's what they use at doctors' offices to see like the inside of your body. So the sun does that naturally, but if we had that all the time, like, we would just always have cancer or something wrong with us. We're on our next standard now. So 22.3, describe how properties of air determine patterns of air circulation. Air has four properties that determine how it circulates in the atmosphere: density, water vapor capacity, adiabatic heating and cooling, latent heat release. Density in the mass of air molecules is given volume, which determines the movement of air. Low density air, so warmer air, rises. High density air sinks. It's cooler. Okay, so you know probably from other classes that as things get, as their molecules expand, they tend to have less density. They take up more volume, which means their density gets a little bit lower. Water vapor capacity determines air circulation and water vapor retention. Warm air is less dense and can absorb more water vapor than cool air. Okay, so you know that from being hot and humid. You live in Missouri, our summers are typically hot and humid, so our warm air holds a lot of water vapor, which causes us to be sticky and humid. Okay, where the closer you get to like Florida or Alabama, you know that air is going to be hot and humid. Okay, because that warmer air is going to hold a lot more moisture. The maximum amount of water vapor that can be in air at a given temperature is called its saturation point. Okay, so this is a nice little graph that shows saturation points of different gases. So 20 grams of H2O per meter squared would fall as precipitation at level 2. So the saturation point looks like 30 right here. And after that, it's going to start falling at 10 degrees Celsius. Whereas here at 50 degrees, it can hold 80 grams of water before it's going to start to rain. So that's all that means. So as the temperature goes up, the air can hold more water vapor. When the temperature goes back down, you're going to start seeing more precipitation at lower temperatures. As air rises higher in the atmosphere, the pressure decreases, and the air that's rising, as air rises higher in the atmosphere, the pressure decreases, allows the rising air to expand in volume, which ultimately lowers the air temperature. So as the air is getting warmer, it's going to rise, and eventually the volume will expand, which means that energy can dissipate, and the temperature is going to become lower. The cooling effect and the reduced pressure on this air as it rises in the atmosphere and expands is called adiabatic cooling or adiabatic cooling. The heating effect of the increased pressure on the air as it sinks towards the surface of the earth and decreases in volume is called adiabatic heating. Okay, so the cooling effect reduces the pressure on the air as it rises, and this causes it to expand, which means whenever it expands, that energy is dissipated, so that air is going to cool and start to fall back, right? The heating effect, so the increased air pressure as it sinks towards the surface of the earth, is a decrease in volume, so all the energy is coming back together, and that's making it warm up. The last property of air determining circulation is the production of heat when water vapor condenses from a gas to a liquid. So, precipitation. The release of energy when water vapor in the atmosphere condenses into liquid water is called latent heat release. So, the energy that's released whenever it rains is called latent heat release. Okay, we're on our 22.4. Explain what drives atmospheric convection currents. So, atmospheric convection currents are global patterns of air movement that are initiated by unequal heating of the Earth. Regions near the equator receive more solar radiation regions than near the poles. As air absorbs and releases heat, it rises and falls all over again. So, the best example I can think of this is that lava lamp. So, we'll start here. So, cold, dry air is displaced horizontally and sinks back to the Earth's surface. As it sinks back to the Earth's surface, you have that adiabatic heating, warms dry air that sinks down to the Earth's surface. So as it comes back down, it's getting warmer. Okay, because it was cool, and as it gets to the Earth's surface, it's heating back up. Hot, dry air picks up moisture because we know that hot air can hold more moisture, and then it starts to rise again. Humid air at the Earth's surface warms and rises. You guys know that hot air rises. That's a common fact. Okay, and then the cooling starts to take place, so that air molecules start to spread out. And as the air cools, it can only hold a certain amount of water. So that causes condensation and then precipitation of our water vapor. That latent heat release causes the air to again become hot. and then it reaches a certain point where the volume expands and it starts to become cool again, and then that cool, dry air starts to process over again. So again, it's just like it's kind of like a reverse lava lamp. So it gets warmer over here, and then it starts to go up and get cooler, and then it falls back down when it's warmer. Whereas a lava lamp gets hot, comes up here, cools down, and come back. So it's like a backwards lava lamp is our atmospheric convection currents. So the warmer it gets, the more it rises. The colder it gets, that falls to the surface. Along the way, it's going to lose and gain water vapor and cause precipitation and condensation. So atmospheric convection currents on Earth are found at specific latitudes due to the following the previous pattern. So it's talking about this. So that's convection currents. Okay, the Hadley cells are convection currents that cycle between the equator at 30 degrees north and 30 degrees south. Okay, so that's on either side of the equator. The circulation of the Hadley cell is driven by intense solar energy near the equator. At the latitude with most intense sunlight, two of these Hadley cells converge, leading to the intertropical convergent zone. So that should tell you kind of where these things are located. So 30 degrees north, 30 degrees south, it's going to be in that tropical zone where you're going to find a lot of your tropical climates, such as beaches and things like that are warm in our tropical rainforest. So looking at this graphic, at the intertropical convergence zone, the sun heats the tropical air, causing it to rise. Then we go to step 2. The air rises, experience adiabatic cooling, and which causes the warm air vapor to condense and fall back to the earth. Number 3, the condensation of water vapor produces latent heat release. So then it's going to release heat, and then it's going to expand. Further up in the atmosphere, the warm air rising displaces the colder, drier air, and that moves that air back down. The cold air sinks and experiences adiabatic heating, which reaches the Earth's surface and warms as dry air, and then flows back to the equator. So if you've ever been on a vacation to Florida or Georgia or Alabama or Mississippi, you know that it rains probably like once a day on average, not for very long, but they experience these Hadley cells very often. And so it's just a constant rotation of air molecules getting warmer and rising, and then raining, and then displacing the other colder air, making it come back down, getting warmer, rising, colder, coming back down. Okay. So another set of atmospheric convection currents occur near the poles. These polar cells are convection currents formed by air rising at 60 degrees north and 60 degrees south, at sinking at the poles at 90 and north and 90 south. Okay, so this is like Canada and the Arctic and the Antarctic. The third convection current is known as the Ferrel cells, which are those convection currents found between the Hadley and the polar cells. So that's kind of where we are. Together, these convection currents move warmer air from tropical regions to mid-latitudes and polar regions, having a large impact on locations of biomes globally. So there's not a good image of that, but if we were looking at the Earth, let's see if I can find one. So your 30 degrees is going to be kind of in this area, and then 30 degrees will be like right here, so it tells you. And those Ferrel cells are going to be hanging out right here and here in the Fertile Crescent area. Okay, so now we're on to our last unit to explain the Coriolis effect, alters how it affects global wind directions. So convection currents normally cause air to move directly north or south, but the Earth's rotation affects this. The Coriolis effect is the deflection of an object's path through the Earth's rotation. The deflection occurs moving north or south because the larger circumference of the equator causes air to move faster than it does at the poles. Okay, so if you didn't know this, the rotation of the Earth, things that are in the middle, so the equator, is actually rotating at a faster speed than things at the poles because the diameter is much bigger here. So for you band kids, if you've ever had to march in a parade and around a corner, you know that people on the inside don't have to move as much, whereas the people on the outside have to move a lot more because they're trying to keep in a straight line. Same thing with our rotation here. So the bigger you are in the middle, the more it has to move, whereas you don't have to move as much or as quickly on the outsides of it, so north and south. And what that does is instead of the winds going just up and down, as they're moving through their convections, the Earth is rotating, so it's causing things to go um, in this direction, and because we move this way, and so it's causing like our currents right here that may be in Florida, it's pushing them back into like Mississippi and Alabama, across Texas and Mexico, all the way to California. And then the same thing is happening here. And so the best thing that they talk about is if you were to travel from the North Pole to the South Pole and you try to go in a straight line, so you hit like a baseball and you try to go here, the baseball is not going to end up exactly where that straight line path would be, because the Earth rotates. So it's going to end up about a couple degrees off of where you actually hit it in a straight line, because the Earth is rotating pretty quickly, especially around the equator. So if you didn't know, again, the Earth rotates a lot slower at the poles than it does at the equator. So 291 kilometers an hour up here, and at the equator, it's 1,670 kilometers an hour. And again, to give you a comparison, a kilometer would be the closest to the English mile. So the Coriolis effects explain prevailing wind directions and how deflection occurs according to the latitude. So back whenever your main way of getting across the world was sailing, sailors would use this information to get around the Earth. So you can see the northwest trade winds are going to blow on the equator at an east or a west direction. No matter where you came from, you're always going to probably go west. Whereas if you got to the westerlies, it's going to actually blow you east. And then no matter if you're on the southern westerlies or the northern westerlies. Okay, so if you were coming from England, you're probably going to travel closer to the equator, which makes sense on how people ended up in Cuba and South America. And then as you would head back to Europe, you would sail more in this direction, because that's the way the wind would take you. And all of that is caused by the different cells here, along with the rotation of the Coriolis effect. And it's causing these currents to consistently blow in these directions. Okay. So if you are in the equator area, you're going to be always going in a west direction of the wind. If you are in the Tropic of Cancers, you're going to be going in an east direction, so it's easy to navigate. And then if you're up at the top, you're going to have just some vortexes that are going to blow you just around where you're going. Like I said, this is a big unit, so let's double check that we hit all of our standards for this unit. And then I'll let you go. Let me know if you have any questions. So why does the amount of solar radiation vary with latitude and the seasons? So again, looking at this first standard right here. The equator receives more solar radiation because it receives the sun rays at a perpendicular angle to the Earth. So the sun's rays travel a shorter distance through the atmosphere and is distributed over a smaller area at the tropics than near the poles. The tropics can also absorb more of the sun's energy because they have a lower albedo values than the polar regions. So that means that they will absorb more heat. Because Earth's axis is rotated at 23.5 degrees, Earth's orbit around the sun causes most regions of the world to experience seasonal change in temperature and precipitation. Our second standard: what are the major gas layers in the Earth's atmosphere? So nearly 99% of the atmosphere is comprised of nitrogen and oxygen. The remaining 1% is a mixture of scarce gases, such as greenhouse gases, that play an important role in determining temperatures on the Earth. There are 5 layers of the atmosphere. The troposphere is the layer closest to the Earth and is layer with our weather and where our weather occurs. The next layer is the stratosphere, which contains ozone that absorbs the most of the sun's ultraviolet B and ultraviolet C radiation. The other layers are the mesosphere, thermosphere, and the exosphere. Our third one is, how do the properties of air determine patterns of air circulation? Air density affects whether it rises or sinks in the atmosphere. Less dense air rises and denser air sinks. Warm air can contain more water vapor than cold air. Air pressure affects how air warms and cools. Reduced pressure leads to adiabatic cooling, whereas increased pressure leads to adiabatic heating. When water vapor condenses into liquid, there is a latent heat release, causing the air to become warmer. Our fourth standard: what drives atmospheric convection currents? The 4 properties of air combined with the most intense solar radiation near the equator drives the Hadley cells. Hadley cells rise near the equator, and the air cools, and the air releases water as precipitation. The cold air The cold, dry air sinks back to the Earth near the 30 degrees north and 30 degrees south latitude. As it sinks in, becomes warmer. The movement of these Hadley cells helps drive the circulation of air in the ferrule cells and the polar cells. And then finally, how does the Coriolis effect alter the global wind direction? The rotation of the Earth on its axis causes points to the equator to spin much faster than points near the poles. As a result, air movement from the Hadley, ferrule, and polar cells near the planet's surface are deflected east or west. The combination of this convection current and the Coriolis effect produces winds that differ in direction from different latitudes. So that's your 5 learning goals. Let me know if you have any questions.